Nickel mines fuel the world's push for renewable energy, but in Morowali, they've poisoned rivers and left children sick. Witnessing this firsthand, I couldn't ignore the cost of progress built on environmental harm. I'm Emily, an aspiring environmental engineer, but my very first project wasn't engineering related. It was about mapping the 2018 liquefaction disaster in my city, where entire neighborhoods collapsed after being built on unstable ground. Through research, we found that the area's place names had hinted at geological risks, signals that were overlooked in planning. It was when I realized how much is at stake when science isn't integrated into decision making. That experience shaped how I see engineering as a responsibility to protect communities, from co-developing a low-cost coffee bean sensor that supports local roasters to leading a team that gamified UN SDGs to make climate literacy more accessible in under-resourced schools. The methods differ but share one goal: turning innovation into impact to bridge vulnerable communities. That commitment and Indigo Research's own mission of making research accessible to all formed the perfect foundation for my journey. Why bring up the nickel paradox then? You see, while preparing for a debate competition on sustainability, I discovered that although nickel is crucial for lithium-ion batteries powering electric vehicles and renewable energy storage, its extraction often depends on coal and causes deforestation, rain pollution from tailings, and displacement of local communities. So here's the million-dollar question: how can Indonesia transition from a high-impact nickel extraction to a cleaner circular production model without sacrificing its role in the global battery supply chain? To tackle this, I will focus on HPAL and the DNI, two hydrometallurgical methods that promise lower emissions and higher efficiency compared to traditional smelting. While these technologies are often studied in a controlled lab environment, their real-world viability in Indonesia's laterite-rich mining regions remain underexplored, particularly for lower-grade ores that are abundant but economically overlooked. My work will investigate whether modular, scalable versions of these refining techniques can operate sustainably within Indonesia's industrial and environmental constraints. By collaborating with Dr. Justi and Dr. Carol, I'll leverage their expertise in adaptive systems and modular robotics to explore how decentralized refining units could minimize reliance on large polluting smelters. Dr. Carol's work on reconfigurable robotics inspires my vision for portable HPAL systems that could be deployed across mining sites, while Dr. Justi's research in design may give insights to handle Indonesia's variable ore compositions. Through computational modeling and feasibility analysis, I'll develop a framework to validate these technologies' scalability, providing actionable insights for policymakers and industry leaders. Indonesia's challenges are complex, and I know I can't solve them alone. IRIS Next Gen Scholarship will help me learn how to turn my ideas into a blueprint for sustainable mineral extraction that other nations could adapt. This work will lay the foundation for my long-term goal of becoming a renewable energy systems engineer dedicated to equitable access in Indonesia. And that's why